Okay, so good afternoon to everyone. Welcome to lecture number 10 of the course Decifri Strengths in Modern Cryptography. I am Marco Timpanella from the University of Perugia, and today we will see a brief introduction to the theory of error correcting codes, and in particular how this theory applies to post-quantum cryptography with the so-called code-based cryptography. This will be the topic of this lesson and also the next one. And in particular, today we will focus on problems in coding theory that turn out to be useful for cryptography. Then in the next lecture, you will see some crypto systems that are based on these problems. So let me start with a brief introduction to coding theory. First of all, one may ask, why do we need coding theory? To answer to this question, consider the situation described in this picture here. So as you can see here, there is a message X that we want to send through a certain communication channel. But the problem of every communication channel, a big problem, is that they are noisy, meaning that what you send is not always what it is received, because there may be errors that occur during the communication. And so to avoid this problem, to deal with this problem, the basic idea behind coding theory is to add the redundancy to the message X that we want to send in a particular way, such that sometimes we are able to reconstruct the original message, even if an error occurs. So this approach is described in this picture. We start with the message X. The first step is to apply an encoding algorithm, meaning that we transform our message X into a longer vector C by adding a redundancy. And this vector here is called a code word. Then the code word is sent through the communication channel, and at this point, a certain error may happen. The last step of this process is to apply a decoding algorithm that tries to estimate the received vector Y, which may be affected by the error E. And well, at the end, hopefully, the estimate of the message is exactly the message that we sent at the beginning. So this is the general picture, but then the problem is to find smart ways to encode and decode. Let's look at a very easy example, the so-called repetition code. This code follows a very simple rule. That is, whenever we want to send the bit 0, assume that we send 5 zeros instead. And the same for the bit 1. So we are adding a redundancy to the message. Now, assume that after a certain communication, you receive this vector here, 0, 1, 0, 0, 0. What can we say? Why this redundancy works for error correction? Well, the first thing that we can say is that for sure there was an error in the communication, because this vector is not the all 0 vector and is not the all 1 vector. So there is, first of all, an error detection. But actually there is also an error correction, because we can guess that the correct code word that was sent by our friend was the code word with all zeros. This is an estimate that we make basically by majority vote. So this very easy example already works. Now, let me observe that this very easy code C made by two code words can be described in this particular way here, where G is a certain matrix. In this case, it is a 1/5 matrix, this one. And in general, when this happens, when we can describe a code by means of a matrix, we say that this code is linear. And linear codes are a fundamental class of error correcting codes, in which in particular we will be interested today. So here you can see the formal definition of linear codes. We will say that an NKQ linear code is a k-dimensional linear subspace of FQ to the n. If this happens, n is the length of the code and k is the dimension of the code. Also, if q is 2, we will say that the code is binary, is a binary code. As I said, this class of codes can be described using matrices, and we say that a generator matrix for a certain code is a k by n matrix whose rows are a basis for C, and we have then this description here. If we go back to the example of the previous slide, the repetition code, we can say with this new terminology that that code was a 5-1 binary linear code. There is a microphone open. Okay. So yeah. Now, whenever we have an NKQ linear code, we can generate another linear code, the so-called dual code of C, which is denoted by this symbol and defined in this way. So it's the set of vectors of fq to the n whose scalar product with all the code words is 0. If you define this object, it is easy to see that it is actually a vector space, and it defines a linear code with dimension n minus k and length n. So we have a new code. We can consider a generator matrix for this code, the dual, and this generator matrix is called a parity check matrix for C. And also parity check matrices allow a description of our code. In the case of the repetition code of the second slide, this matrix H is a parity check matrix. Okay, so now if we have a code, an NKQ linear code, it is easy, it is always easy, and it is clear how we encode messages. It is much more difficult the decoding problem, that is, given a vector in fq to the n that we receive, how do we understand which is the code word that was originally sent? This is a much more difficult problem. And a possible approach to this problem consists in first defining a distance between vectors of fq to the n, the so-called Hamming distance, defined as the number of coordinates at which two vectors differ. And once we have this concept of distance in fq to the n, it is natural to decode a certain vector with the code word that minimizes the distance, the Hamming distance from y. Okay, this is a very natural approach, and it is called the nearest neighbor decoding rule. We can also ask now how many errors a certain code can correct. We can answer to this question defining another parameter of a linear code, a key parameter that is called the minimum distance of C, defined as the minimum among the Hamming distances of two distinct code words. It is possible to prove that if a linear code C has minimum distance D, then it can correct up to this number here of errors. As a terminology that I will use, I will say that the weight of a vector is the Hamming distance between that vector and the zero vector. Okay, so now we have introduced all the three key parameters of a linear code, the length, the dimension, and the minimum distance. And so we can ask which are the best codes that we can construct. Observe that if we fix the length of the code and the dimension of the code, then our aim would be to maximize the minimum distance, because of course we want to correct as many errors as possible. But on the other hand, if we fix the length and the minimum distance, we want to maximize the dimension of the code because we want as many code words as possible. So what can I do? What is the best that I can do? Well, there are several bounds that answer to this question in coding theory. Here you can see two famous bounds. The first one is the singleton bound, saying that if we fix the length and the dimension of a linear code, I cannot have a too large minimum distance, because this distance is at most n minus k plus 1. In particular, if a code here attains the equality, then it is called MDS. And so these codes are basically optimal with respect to their error correction capability. The other bound that you can see here, the Gilbert-Varchamov bound, is slightly different because it says that if you fix three numbers, n, k, and d in this way, and these three numbers satisfy this numerical condition, then there exists a linear code of length n, dimension k, and minimum distance at least d. So it is an existence result. Okay, this was an introduction. Now let's go back to the key problem for cryptography, the decoding problem. Let me repeat that in general, the encoding is always easy. Decoding is a difficult problem. So this can be seen as a sort of mathematical trap. It is a sort of one-way function. So we can try to use this mathematical trap in cryptography, and the type of cryptography that tries to exploit this trap is the so-called code-based cryptography. To be more specific about the decoding problem, it was proved by Berlekamp and others that if you take a random code, so basically you take a random matrix, then the problem of decoding that code is NP complete. So it is very, very difficult. On the other hand, if you construct a code in a particular way, so with a lot of mathematical structure, the so-called algebraic codes, then efficient algorithms may exist. And this is what we will see in a few minutes. Let's start from the random case. Okay, so what can we do with a random linear code? Well, the trivial solution, the naive solution, would be to make a table writing down for every vector of fq to the n, which is the nearest code word. This table, of course, solves the problem, the decoding problem, but this is actually practical when the parameters of the code are large, because the size of this table is q to the n. It is possible to improve the naive solution with the so-called syndrome decoding algorithm. This algorithm is based on a few observations that you can see here. The first observation is that if you have a linear code, then the cosets x plus c partition the whole space in a certain number of sets, q to the n minus k, of size q to the k each. So now you have this partition of the space, and something that you can do is look at each of these cosets and pick a code word, a vector of smallest weight possible. This vector is called the coset leader of that coset, and by definition, the weight of a coset is the weight of a coset leader. This coset leader may not be unique, though. Okay, another key observation is the following, that if you take two vectors in fq to the n, they belong to the same coset, so to the same element of the partition, if and only if this equality holds, where H is a parity check matrix. And this value here is called the syndrome of a certain vector. So by this observation, the syndromes are constant in a certain coset. Okay, how can we apply these observations to the decoding problem? Well, assume that we send a certain code word C, and that Y is the received vector that may be affected by an error. Applying the nearest neighbor decoding that we have seen before is equivalent to finding a vector of smallest weight possible with the property that this difference is a code word. But this, in terms of cosets, is equivalent to finding a coset leader of the coset that contains the received vector y. So this is a reformulation in terms of cosets, and by this observation, we can decode following three steps. The first step is a sort of pre-computation phase where we make a table. And in this table, we want to write down for each syndrome the coset leader of the coset with that syndrome. We know that there is this bijection between cosets and syndromes, so we can do that. And so we can write down a table with this information. At this point, that's it, because to decode Y, we simply have to compute the syndrome of y. And then we know which is the coset leader of the coset with that syndrome, and the decoding of y will be y minus that coset leader. So this is quite easy. And what is the improvement with respect to the naive solution? Well, the improvement is that here we have a table of size q to the n minus k and not q to the n. So this is a good improvement, but still it is exponential, so it is still unpractical for large parameters. Okay, let's move to the algebraic setting. The class of linear codes in which we are particularly interested in this setting is the class of cyclic codes. The reason is that for cyclic codes, we have very efficient decoding algorithms, as we will see. Now, first, let's see the definition. A linear code is cyclic if it has the following property, that whenever you take a code word and you take a shift of that vector, the shift is still an element of C. This is the property of cyclic codes. It is particularly interesting to look at this correspondence in the case of cyclic codes, that is to associate vectors of fq to the n to polynomials with coefficients in fq in this easy way. Why is it useful? Because compute the polynomial x times c of x. So you end up with this polynomial here. Now, if you can replace x to the n by 1, then the polynomial that you obtain is exactly the polynomial associated with this vector here. So basically, by replacing x to the n equals to 1, we have a way, a mathematical way to interpret the shift of a vector. And this means, this observation means that cyclic codes correspond to ideals in fq of x over x to the n minus 1. We take this quotient because we want to replace x to the n by 1. We know many things about cyclic codes. For instance, they are always generated by a divisor of x to the n minus 1, and this polynomial g here is called the generator polynomial. And we also know that the dimension of these codes is n minus the degree of the generator polynomial, and we know how to write down a generator matrix of the code in terms of this generator polynomial. So we have many information. Okay, let's look at some families of cyclic codes. I want to start from the easiest, but also the most important class of cyclic codes, that is Reed-Solomon codes. To define these codes, take n as q minus 1. This will be the length of the code, so here q has to be greater than 2. Take a primitive element of fq, alpha, and an integer delta between 2 and q minus 1. Then you can consider this polynomial g delta of degree delta minus 1, and the Reed-Solomon code with parameter delta is the cyclic code generated by this polynomial g delta. If you look at the theorem of the previous slide, you will easily deduce that this code is a code of dimension q minus delta, length q minus 1, and it is also possible to see that the minimum distance is exactly delta. And so if you make the computation, you see that this code is an MDS code, so it is optimal. Okay, now, starting from this definition of Reed-Solomon code, we can define a first generalization of Reed-Solomon codes, that is the class of BCH codes. To provide this generalization, take n as q to the m minus 1. Now, alpha is a primitive element of fq to the n. Take delta as before, between 2 and n. And as a notation, I will denote with this symbol the minimal polynomial of alpha to the I over fq. Now, if you replace the polynomial G delta of the previous slide with this polynomial here, so the least common multiple of the minimal polynomials of alpha, alpha squared, alpha to the delta minus 1, then you end up with another cyclic code, and this cyclic code here is the so-called BCH code with parameter delta. Why is this a generalization of the previous class of codes? Well, if you take m equals to 1, then alpha is a primitive element of FQ, and so we know the shape of these minimal polynomials, and so simply by this definition we find exactly the polynomial G delta of the previous slide. Finally, we have some information on the parameters of BCH code. We know the length, and we have some lower bounds on dimension and minimum distance. Okay, let me go back again to Reed-Solomon codes. The reason is that I want to show you another generalization of Reed-Solomon codes that arises from another definition, equivalent definition of Reed-Solomon codes. So let's look at this definition. Here, the first 3 points are as before. Take this vector space LK, that is the polynomials coefficients in FQ of degree at most k. Then you can define this object here, that is, you take n tuples obtained by evaluating polynomials of degree at most q minus delta minus 1 at alpha, alpha squared, and so on up to alpha to the q minus 1. This is a new object. This is a vector space, a linear subspace of Ft to the n, because the evaluation map is linear. And it is possible to see that this new object is exactly the Reed-Solomon code that I defined at the beginning. So this is an equivalent definition. It is also very easy to see with this definition that the code is MDS simply by looking at the zeros of these polynomials that are bounded. And from this definition, the next generalization comes very natural. This is the definition of generalized Reed-Solomon codes. That is, take k and n in this way, and take 2 vectors, a and b. So a is a vector of n distinct elements of FQ, b is the vector of n non-zero elements of FQ, so they may be also equal. Then the generalized Reed-Solomon code arising from this choice is obtained again by evaluating polynomials at a1, a2, an, but this time we also multiply by b1, b2, bn, each entry. And so this is clearly a generalization corresponding to this particular choice of a and b, and this is still an MDS code. The last class of cyclic codes that I want to show is the one of classical Goppa codes. This is crucial in code-based cryptography, as you will see. So to define it, take a positive integer m and a polynomial with coefficients in FQ to the m of degree t. Take some elements of FQ to the m at which g does not vanish. The Goppa code associated with this choice is the linear code arising from this parity check matrix. And also in this case, we have some lower bounds on the parameter of the code. As you can see, it depends on this choice of L and also on the polynomial G. There are several relations between these codes that I introduced. To understand this relation, let me give this definition. That is, if you have a linear code over a certain extension of FQ, something that you can do is to take only the code words that have coordinates in FQ. It turns out that this is another linear code. This is called the subfield subcode of C. We have again information on their parameters, and it is possible to prove that the classical Goppa codes are subfield subcodes of generalized Reed-Solomon codes, and that BCH codes are subfield subcodes of Reed-Solomon codes. This fact is also important for code-based cryptography, and you will see that. Okay, I want to show an example of efficient decoding. This example works for BCH codes. Of course, because of the time, I can only show one efficient algorithm, but there are many. So this is simply the setup for defining a BCH code. Assume that you receive a certain vector y. Okay, here we are in the polynomial setting, so you receive a certain polynomial y that is a certain code word c plus a certain vector, error vector. So if this error vector is non-zero, then we need to decode y. And one way to do that is to use the so-called Peterson-Gorenstein-Zierler algorithm, an algorithm that allows to correct efficiently up to this number of errors. So let's see how it works. Assume that our error polynomial has not too many, has weight not too large. So let's say that v is the weight of this vector. So it means that the polynomial has this shape. We want to find this polynomial in order to decode. So we want to find both these coefficients, eki, and we also want to find the exponents of this polynomial. If we find these numbers, then we find the error vector and we are able to decode. But how can we do that? The first step is to compute the syndromes, the so-called syndromes, that is the evaluation of the received vector y at alpha to the I. And by definition of cyclic code, these values are exactly the values that the error vector has at alpha to the I. So if we write down all these equations, we end up with a system in two variables, two types of unknown, the ej's and the xj's, that are linked to the ekj's and to these exponents kj's. We would like to solve this system, of course, but the problem is that this system is non-linear in the xj's and we don't know both of them. So it is too difficult. We need to do something more. So we introduce a new variable that is this polynomial here, sigma x. From the definition of this polynomial, you can see that the roots of sigma x are the inverse of the unknowns x1, xv. And if you write down this polynomial in a certain shape and you make some computations that I will skip, you end up with these equations in red. So basically, you end up with another system in other unknowns. And the key part of the algorithm is to solve this system here. This is not easy, but it can be done with some algorithms that you can see here. So let me show how we can decode if we can solve this system. Because assume that you know sigma 1 up to sigma v. This means that you know exactly this polynomial, sigma x. But if you know sigma x, you can also, by brute force, you can find the roots of the polynomial, and finding the roots of this polynomial sigma x is equivalent to finding these unknowns xj. So now we have part of what we wanted, but now if we know xj, we can go back to the equation, to the system with the equations in blue, and now we want to look for ej. In the ej's, this system is linear, so we can easily solve this system, and so we end up with ej and the xj, so we know the error vector, and we can finally decode. This is the Peterson algorithm. Okay, that's what I wanted to say, so thank you. And if there are questions, you can ask, or you can also write by email as you want.